All right, in today's video, we will be talking about bond energy, which I will just abbreviate BE, and bond length. So first we'll deal with bond energy. And let me just give you an example of what that will look like. So if we have a hydrogen molecule, H2 gas, and we break it down into two H gas. Okay, so we've broken the bond. It should be fairly intuitive that in order to break a bond, it requires the addition of energy. Think of it like pulling Velcro apart or pulling two magnets apart. We have to add energy into those systems to break that. So we get what we call a delta H for this equation of 436 kilojoules per mole. So first of all, let me talk about that delta H thing that we have not talked about. That is just the energy of a reaction. We'll talk more about that, I think, in the next couple chapters. But delta H stands for enthalpy, which is just the energy of a reaction. Okay, and this reaction has a positive 436 kilojoules per mole. Well, what does that mean? That means, first of all, the positive, right? We didn't write the positive, but it is positive. That means it is an endothermic process. Endothermic. And that simply means that it absorbs energy. We'll talk a lot more about that later too. And when I say it absorbs energy, one way to remember that would be the word enter starts with an EN, and so does endothermic. So energy enters the system or enters the reaction. And it's also, if we look, it's per mole. And per mole of what? That's per mole of bonds broken. So we started off with H2 gas. That's 1 mole of H2 over here. We broke 1 mole of hydrogen bonds, and we got, and it took 436 kilojoules to break that mole of bonds. So we have to put energy in to break a bond. That makes sense. It takes energy to break something. But what's the flip side of that? What's the opposite case? If we have 2H gas, and we react it to form H2 gas, the delta H of this process, does anybody want to guess? No, nobody wants to guess. Okay. It's negative 436 kilojoules per mole. It's almost like being in person when I can't hear you guys answer anything. Okay, I'm just kidding. All right, so in this process, we release energy, and that's the opposite of endothermic. I'm sure you guys have heard this term at some point. This is an exothermic process because of that negative sign right there. Exothermic. If endothermic absorbs energy, obviously, and exothermic releases energy. And if we stop and think about this, this makes sense that we put energy in to break 1 mole of bonds, so then when we form 1 mole of bonds, we get the energy back out. And it's the same amount of energy because energy is always conserved. Now, if we try to capture that energy, say to produce electricity, we're not going to be able to capture it all because we're going to have loss. Nothing's 100% efficient. But chemically speaking, the energy released is the same as the energy absorbed when we reverse a process. Okay, so let's just look at some various bond energies. Whoops, that's not what I wanted to do. Gosh. I don't think I was made to teach online. I would say I'm too old, but there's older people that do it better than I am. Anyway, let's just look at 4 different molecules and their bond energies. So this is going to look a little bit funny. or H3CH. Let me move that down. Let me just erase the whole thing. Oh my gosh. I hope you guys are laughing. Let me move that down a little bit because I meant to write something else. So H3CH, and what I meant to write was I'm going to have the bond energy up here. Bond energy in kilojoules per mole. Okay, so obviously this molecule, if we were to write out the formula, would be CH4. But I'm writing it this way because I just want to highlight this bond. Okay, I want to highlight the carbon-hydrogen bond. And so if we look at this molecule, specifically methane, CH4, and we look at that carbon-hydrogen bond, it has a bond energy of 438 kilojoules per mole. That means it will take 438 kilojoules to break 1 mole of those carbon-hydrogen bonds. So let's just look at another molecule, F3CH. Again, we're just highlighting that carbon-hydrogen bond. If we were to write out this molecule, we would write it CHF3. Okay. That has a bond bond energy. Sometimes this is referred to as bond dissociation energy. So if I say that, it's the same thing as bond energy. Just depends on who wrote the textbook. That has a bond energy of 446 kilojoules. Just two more examples, very similar. We're just going to replace the halogen with different halogens, and we're going to take a look and see what we have. Every time we're going to look at that carbon-hydrogen bond, though. And here we have 402 kilojoules. And then, interestingly, if we put Cl3 on there instead of something else, yeah, same bond. It's almost identical to bromine, 401. Now, the point isn't to memorize these values. Don't waste your time doing that. I'm not really worried about that. The point is to highlight that they can be different. A carbon-hydrogen bond will be different depending on the chemical environment it's in or the molecule it's associated with. But what we can do is we can measure lots of these, hundreds of them, and we can average them. So we can look at an average carbon-hydrogen bond, and we find that the average is 414 kilojoules per mole. So if you look these up on the homework, if you're looking them up for the homework, they will vary slightly depending on source. So I'd recommend just going with the values the homework gives you when you are doing homework. Obviously on the exam, they will be provided for you. No need to memorize them. Okay, so we are always going to deal with averages. So let's just look at one more thing with regards to bond energies, and then we'll talk about lengths very briefly. I'm just going to give you 3 bond energies. Again, bond energy, kilojoules per mole. And for a nitrogen-nitrogen bond, a single bond that is, this is, I'm having trouble today, aren't I? 163 kilojoules per mole. A nitrogen-nitrogen double bond, 418 kilojoules per mole. And a nitrogen-nitrogen triple bond would be 946 kilojoules per mole. So we can see a general trend here. And this holds true pretty much of weakest to strongest. Single bond is the weakest, triple bond is the strongest. That makes pretty good sense. Now if we look at the bond length of those, and these are measured in picometers. If you have to know picometers for an exam, I'll give you the value, don't worry. We have a bond length for the single bond of 145 picometers. For the double bond, it's 123 picometers. And then for that triple bond, it is 110 picometers. So again, we have a trend here, longest to shortest. Triple bonds are shorter than double bonds and shorter than single bonds. So a single bond is weakest and longest. A triple bond is strongest and shortest. All right, that's enough for now.